Today we'll talk about another method of learning called learning by correcting mistakes. An agent reaches a decision. The decision turns out to be incorrect or suboptimal. Why did the agent make that mistake? Can the agent correct its own knowledge and reasoning so that it never makes that same mistake again? As an example, I'm driving and I decide to change lanes. As I change lanes, I hear cars honking at me. Clearly I made a mistake. But what knowledge, what reasoning led to that mistake? Can I correct it so that I don't make the mistake again? Learning by correcting mistakes is our first lesson in meta-reasoning. We'll start today by revisiting explanation-based learning. Then we'll use these explanations for isolating mistakes. This will be very similar to diagnosis, except that here we'll be using explanation for isolating mistakes. This will make it clear why explanation is so central to knowledge-based AI. Then we'll talk about how we can use explanations for correcting mistakes, which will set up the foundation for subsequent discussion on meta-reasoning. To illustrate learning by correcting mistakes, let's go back to an earlier example. We encountered this example when we were discussing explanation-based learning. So imagine again that you have bought a robot from the Acme hardware store, and in the morning you tell the robot, go get me a cup of coffee. Now the robot already is bootstrapped with knowledge about the definition of the cup. A cup is an object that is stable and enables drinking. The robot goes into your kitchen and can't find a single clean cup. So it looks around. This is a creative robot, and it finds in the kitchen a number of other objects. One particular object has this description. The object is light and is made of porcelain. It has decorations and it has concavity and a handle, and the bottom of this object is flat. Now the robot decides to use this object as a cup because it can prove to itself that this object is an instance of a cup. It does so by constructing an explanation. The explanation is based on the fact that the bottom is flat, that it has a handle, that the object is concave, and that it is light. Let us do an exercise together that will illustrate the need for learning by correcting mistakes. So shown here are 6 objects, and there are 2 questions here. The first question is, which of these objects do you think is a cup? Mark the button on the top left if you think that a particular object is a cup. The second question deals with the definition of a cup that we had on the previous screen. So mark the button on the right as solid if you think that that particular object meets the definition of the cup in the previous screen. What do you think, David? Which one of these is a cup and which one of these meets the definition of the cup on the previous screen?
So according to my intuitive definition of a cup, 3 of these objects are cups. The object in the top right is not because that's a potato masher. The object in the top left isn't because that's a little pail. And the object in the bottom middle is not because that's actually a candlestick holder. According to the definition of a cup that the robot was bootstrapped with, however, only the potato masher doesn't meet the definition. All 5 of these objects have flat bottoms, they all have concavity, they're all light, and they're all liftable. We might not think that the candlestick holder is liftable because it doesn't have a handle, but we might also think that it's liftable because it's light enough, so either way would work for that. But it's clear that the pail up here meets all our definitions for a cup. But it's clear that the pail meets all our requirements for a cup, but is not actually a cup.
Let us build on David's answers. Let us suppose that the robot goes to the kitchen and finds this pail in the kitchen. It looks at the pail and decides that this pail meets its definition of a cup, denoted here by the solid circle. The robot brings water to you in this pail. You look at the pail and you say to the robot, "No, robot, this is not a cup." At this point, you would expect the robot to learn from its failure. Cognitive agents do a lot of learning from failures. Failures are opportunities for learning. We would expect robots and intelligent agents more generally to learn from their failures as well. How then may a robot learn from the failure of considering this pail as a cup? Note that the problem is not limited to this particular pail. We can take a different example connecting with this particular cup. Imagine that the definition of cup included the statement that it must have a handle, in which case the robot may not recognize that this is a cup. Later on, you may teach the robot this in fact is a good example of a cup because it's liftable. In that case, the robot may want to understand from that failure, it may want to understand why did it not consider it to be a cup. It should have considered it to be a cup. So the problem is not just about successes that turned out to be failures, but also about failures that should have been successes. So the question then becomes, how might an AI agent learn from its mistakes? Learning by correcting mistakes or learning from failures really entails answering 3 separate questions. The first question is, how can the agent isolate the error in its form or model? So the agent had some model of the world. It made a mistake based on its model. How can it identify the error in its model? Note that this particular problem is very closely connected to the question of diagnosis that we discussed earlier. The second question is, how can the agent explain to itself that the fault it has identified, the error, in fact led it to the problem, to the failure? Having identified the fault and explained how the fault led to the failure, the third question is, how can the agent repair the fault in order to prevent the error, the failure, from reoccurring? You may have noticed that earlier we had related learning by correcting mistakes with metacognition. You can see how that relationship occurs. The agent has some knowledge of the world. That knowledge leads it to failure. The agent is using that failure to repair its own knowledge. It is as if the agent is looking into itself, looking into its own reasoning, into its own knowledge, and correcting itself. Note once again that the learning here is incremental. We are learning from one example at a time. However, instead of simply learning from an example, we are also using explanation-based learning. We are trying to explain why a particular fault led to a particular failure. That explanation connects then with explanation-based learning, not just with the notion of incremental learning. Let us see how these three questions occur in the example of the pail. The first question is, how can the agent identify that the fact that this particular pail has a movable handle, not a fixed handle, is why this is not a good example of a cup? The second question is, how can the agent build an explanation that proves why having a movable handle makes this a poor example of a cup? Why does that lead to a failure? The third question is, how can the agent change its model of a cup so that it never again picks an object with a movable handle as an example of a cup?
So when we talked about explanation-based learning, we used another example of this as well. We imagined a desktop assistant that I can just say, hey, fetch me that important file from last Tuesday, and it can construct its own understanding of what file I might be talking about. It has a notion of what files have been important in the past and certain criteria of those files, so it constructs an understanding of what important is, and then tries to transfer that onto files from last Tuesday. Now imagine that I told this agent, hey, fetch me that important file from last Tuesday, and it returns me a file that actually wasn't important. And I say, hey, that file isn't actually important at all. The agent would first try to isolate what error it made in diagnosing that particular document as important. It might, for example, notice that every other document I've ever labeled as important was very recent, whereas this one was very old. So even though it met all the criteria for an important document, there might be more criteria that it didn't consider yet, and one of those might be that only new documents are very important. It would then explain that the problem came from the assumption that an old document could be important, and it would then repair its model to say that in the future, old documents can't be important, even if they meet the other criteria for importance.
This problem of identifying the error in one's knowledge that led to a failure is called credit assignment. Blame assignment might be a better term. A failure has occurred. What fault or gap in one's knowledge was responsible for the failure? That's blame assignment. In this lesson, we'll be focusing on gaps or errors in one's knowledge. In general, the error could be in one's reasoning or in one's architecture. Credit assignment applies to all of those different kinds of errors. Several AI theorists, Marvin Minsky for example, consider credit assignment to be the central problem in learning. This is because AI agents live in dynamic worlds. Therefore, we will never be able to create an AI agent which is perfect. Even if we were to create an AI agent which had complete knowledge and perfect reasoning related to some world, the world around it will change over time. As it changes, the agent will start failing. Once it starts failing, it must have the ability of correcting itself, of correcting its own knowledge, of correcting its own reasoning, correcting its own architecture. You can see again how this is related to metacognition. The agent is not diagnosing some electrical circuit or a car or software program outside. Instead, it is self-diagnosing, self-repairing. As we mentioned previously, in general, the errors may lie in the knowledge, in the reasoning, or in the architecture of an agent. And therefore, learning by correcting errors might be applicable to any one of those. However, in this lesson, we'll be focusing only on errors in knowledge. In fact, in particular, we'll be focusing on errors in classification knowledge. Classification, of course, is a topic that we have considered this class repeatedly. Let us consider an AI agent that has two examples of executing an action in the world. In the first experience, the agent views this object as a cup and gets the feedback this indeed was a cup. So this was a positive experience. This, on the other hand, is a negative example. Here the agent viewed this as a cup and got the feedback that this should not have been viewed as a cup. We can visualize the problem of identifying what knowledge element led the agent to incorrectly classify this as a cup as follows. This left circle here consists of all features that describe the positive example. The circle on the right consists of all features that describe the negative example. So features in this left circle might be things like this is a handle, there is a question mark, there is a blue interior, and so on. The circle on the right consists of features that characterize the negative example. It has a movable handle, it has a red interior, it has red and white markings on the outside. There are some features that characterize only the positive experience and not the negative experience. There are others that characterize only the negative experience and not the positive experience. There are also many features that characterize both the positive and the negative example. For example, they are both concave, they both have handles, and so on. In this example, it is these features that are especially important. We'll call them false suspicious features. We call them false suspicious features because first, they identify only the negative experience. Secondly, one or more of these features may be responsible for the fact that the agent classified this as a positive example when in fact it was a negative example. As an example, suppose that this feature corresponds to a movable handle. This is a false suspicious feature. It is false because this experience was false. It is suspicious because it does not characterize the positive experience. And thus, it may be one of the features responsible for the fact that this was a negative example. But now there is an additional problem. There are a number of false suspicious features here. So how would the agent decide which false suspicious feature to focus on? We have encountered this problem earlier when we were talking about incremental concept learning. At that point, we had said that we want to give examples in an order such that each succeeding example differs from the current concept definition in exactly one feature, so that the agent knows exactly what to focus its attention on. The same kind of problem occurs again. How might the agent know which feature to focus on? One possibility is that it could try one of the features at a time and see whether it will work. That is, it could select this feature, repeat the process, get more feedback, and either accept it or eliminate it. An alternative method is that the agent may receive not just two experiences, but many such experiences. So if there were other positive experiences that covered this part of the circle, that would leave only this as a false suspicious feature, and then the agent can focus its attention on this feature. As an example, just like this circle may correspond to a movable handle, this may correspond to a red interior because red interior is one of the features that characterizes the negative example and not the positive example. But later on, there might be another positive example that comes of a cup which had a red interior, in which case the agent can exclude this particular feature. Now, the inverse of this situation is also possible. Let us suppose that the agent decides that this is not a cup, perhaps because its definition says that something with a blue interior is not a cup. And therefore, it doesn't bring water to you inside this cup and tells you there is no cup available in the kitchen. You go to the kitchen, you see it, and you say, well, this is the cup. Now the agent must learn why did it decide that this was not a cup. In this case, the relevant features are these three features. These are the three features that define this cup but do not define the other experiences. So this dot may correspond to a blue interior, this dot may correspond to a question mark on the exterior. We'll call these features true suspicious, just like we call them false suspicious. These are the features that prevented the agent from deciding that this was a positive example of a cup. One or more of these features may be responsible for the agent's failure to recognize that this was a cup. Here is an algorithm for identifying what elements in an agent's classification knowledge may be potentially responsible for its failure. Let us look at the problem of identifying the false success elements. As we said earlier, potentially the agent may receive a set of positive experiences and a set of negative experiences, not just one positive or one negative. First, take the intersection of all the features that are responsible for all the false successes. A false success, again, is something that we identified as success but was not a success, like the pail. We identified it as a cup, but it was not a cup. first take the intersection of all the features present for all the false successes. False success is an object that the agent identified as a success, but in fact was false. Like the pail, the agent identified that it was a cup, but it wasn't. Then take the union of the features present for all the true successes. A true success is something that the agent classified as a success and indeed was a success. Now remove all the assertions in the union of the true successes from the intersection of the false successes to identify those elements that are present in the false successes only.
So to put that differently, start off by gathering together anything that's ever present in a false success. Then gather together everything that's true for every single true success. Remove the things that are true for every true success from the things that are ever true for any false success. In that way, we get a list of only the things that are true for some false successes.
Similarly for identifying suspicious true success relationships, except that here the operations are in reverse.
So similarly, here we gather together everything that's ever true about any true success, and then gather together the things that are true for every single false success. So every single false example has these things in common. Then we remove the things that every single false example has in common from the things that are true for any true example.
As you can see, we are taking unions and intersections of features characterizing different examples. The number of examples, both positive and negative, needed for this algorithm to work well depends upon the complexity of the concept. In general, the more features you have in the description of the objects, more will be the number of the examples you will need to identify the features that were responsible for a failure. So let us look at the result of the kind of learning technique we are discussing here. Here might be the old concept of a cup. In this particular case, this particular concept definition has been put in the form of a production rule. Here is the new concept definition for a cup. This is almost identical to the previous definition, except that now the object not only has a handle, but also the handle is fixed. This is similar in many ways to incremental concept learning. You may recall that in incremental concept learning, at any particular stage of processing, there was a concept definition. As new examples came, then the concept definition changed depending on the new example and the current concept definition. Note that in this method of concept revision, the number of features in this if clause may become very, very large very quickly. Here we have object has a handle and handle is fixed. We could keep on adding additional features. The interior is blue that cover all the positive experiences. The difficulty is, at the present time, there is no understanding for why the fact that handle is fixed is an important part of the cup definition. This requires an explanation. Why is it that the handle being fixed is an important part of the definition of a cup? This is one of the key differences between knowledge-based AI and other schools of AI. Classification is ubiquitous in many schools of AI, as we have discussed earlier. Explanation, however, is a key characteristic of knowledge-based AI. Explanation leads to deeper learning. It not only says, here are the features that result in a concept definition, it also says, and here is why these features are important for the concept definition. This brings us to the second question in learning from failures. Now we want the agent to explain why a particular fault in its knowledge led to its failure. You may recall this explanation from our lesson on explanation-based learning. There the agent had constructed an explanation like this to show that a specific object was an example of a cup. For our example of a pail, the agent may have constructed a similar explanation with the object being replaced by pail everywhere. Now, however, the agent knows that pail is not an example of a cup. Something is not quite right with this explanation. We have also just seen how the agent can identify the false suspicious relationship in this explanation. It has identified that the handle must be fixed because that is the feature that separates the positive experiences from the negative experience. The question then becomes, how can this explanation be repaired by incorporating handle is fixed? Where should handle is fixed go? David, what do you think? Where should the agent put handle is fixed in this explanation?
So it seems like the most obvious place to put it would be under the object is liftable connection. In order to make it liftable to enable drinking, it needs to be fixed.
What do you think? Is this a good way to fix the agent's error? David's answer was good, but not necessarily optimal. I think he put handle is fixed at this particular place in the explanation because the first reason here. He wanted to capture the notion that only fixed handle cups enable drinking, and that this part does it. He wanted to capture the notion that only fixed handle cups enable drinking, and this certainly does that. However, this is not an optimal way of fixing this particular explanation. However, this is not the best way of fixing this particular explanation because it leads to additional decisions. It suggests that only those things which have a fixed handles are liftable. But of course, from the pail we know that the pail does not have a fixed handle and yet the pail is liftable. This suggests that handle is fixed should go somewhere else, perhaps above object is liftable but still below object enables drinking. The agent too can figure out that this is not the optimal place for putting handle is fixed because A, it violates its notion of a pail. A pail is liftable but has a movable handle. It also violates its notion of a briefcase. This part was coming from its precedent of a briefcase. The briefcase has a movable handle and it too is liftable. This is how the agent knows that its handle is fixed should go somewhere else in this explanation. Above object is liftable, but beneath object is enables drinking. So recall that the agent figured out that handle is fixed should go beneath object enables drinking, but not beneath object is liftable. So the agent may put handle is fixed here in this particular explanation. This is correct. If the agent has background knowledge, which tells it that the reason handle is fixed is important is because it makes the object manipulable, which in turn enables drinking, then the agent may insert this additional assertion here in the explanation. Even more, if the agent has additional background knowledge that tells it that the fact that the object has a handle and that the handle is fixed together make the object orientable, which is what makes the object manipulable, then the agent may come up with a richer explanation. The important point here is that as powerful and important as classification is, it alone is not sufficient. There are many situations under which explanation too is very important. Explanation leads to richer learning, deeper learning. There is one more important point to be noted here. This again is the illustration from incremental concept learning. When we were talking about incremental concept learning, we talked about techniques for learning. We did not talk about how this concept was going to be used. However, in learning by correcting mistakes, we are talking about how the agent actually uses the knowledge it learns. This point too is central to knowledge-based AI for several reasons. The first reason is that knowledge-based AI looks at reasoning, looks at action, decides how knowledge is going to be used, and then determines what knowledge is to be learned. It sets the target for learning. Secondly, you may recall this particular figure for the cognitive architecture that we had drawn earlier. You may see that reasoning, learning, and memory are closely connected, and all of that is occurring in the surface of action selection. This figure suggests that we not only learn so that we can do action selection, but additionally, as we do action selection and we get feedback from the world, it informs the learning. As this figure suggests, intelligent agents, cognitive systems, not only learn so that they can take actions on the world, but further, that the world gives them feedback, and that feedback informs the learning. Once again, failure are great opportunities for learning. One additional point to be made here. Learning by correcting mistakes views learning as a problem-solving activity. An agent meets failure, it needs to learn from the failure. It converts this learning task into a problem-solving task. Let us first identify what knowledge error led to the failure. Then let us build an explanation for this. Then we'll repair it. Thus, learning is closely intertwined with memory, reasoning, action, and feedback from the world. Notice also that the reasoning, learning, and memory here in the deliberation module are closely connected to the metacognition module. Here the reasoning, memory, and learning may be about action selection in the world, but the metacognition module may have its own reasoning, learning, and memory capacities. And some of the learning in the metacognition is about fixing the errors in the deliberative reasoner. So metacognition is thinking about thinking. The agent used certain knowledge to think about the action selection, and it conducted those actions in the world. Metacognition is thinking about what went wrong in its original thinking. What was the knowledge error? We'll return to metacognition in the lesson on meta-reasoning.
So how do you use learning by correcting mistakes to design an agent that can answer Raven's progressive matrices? On one level, this might seem easy. Your agent is able to check to see if its answers are correct, so it's aware of when it makes a mistake. But the knowledge of when it's made a mistake merely triggers the process of correcting the mistake. It doesn't correct it itself. So how will your agent isolate its mistake? What exactly is it isolating here? Once it's isolated the mistake, how will it explain the mistake? And how will that explanation then be used to correct its mistake so it doesn't make the same mistake in the future? Now in this process, we can ask ourselves, Will your agent correct the mistake itself, or will you use the output to correct the mistake in your agent's reasoning? Will you look at what it did and said, here's a mistake it made, so next time it shouldn't make that mistake? If you're the one using your agent's reasoning to correct your agent, then as we've asked before, who's the intelligent one, you or your agent? So today we've been talking about learning by correcting mistakes. We started off by revisiting explanation-based learning and incremental concept learning. In those lessons, we were dealing with a small number of examples coming in one by one. We dealt with the same thing here, but here we had the additional feedback about whether or not our initial conclusion was right or wrong. We then talked about isolating mistakes. This was similar to our problem of diagnosis. Given a mistake, how do we narrow down our reasoning to find exactly where that mistake occurred? Then we talked about explaining the mistake. This is key both to building human-like agents and to enabling the agent to correct its mistake. Only by explaining the mistake can the agent correct it efficiently. And after those phases, correction becomes a much more straightforward task. Next time we'll talk about meta-reasoning in more detail. For example, here we've discussed mistakes in knowledge, but what about mistakes in reasoning? What about mistakes in architecture? What about gaps instead of mistakes, where we don't know something instead of knowing something incorrectly? We'll talk about all that next time.
Learning by correcting mistakes is a fundamental process of human learning. In fact, it may closely resemble the way you and I learn in practice. In our lives, we rarely are passive learners. Most of the time, we are active participants in the learning process. Even in an educational setting like this, you're not just listening to what I'm saying. Instead, you're using your knowledge and reasoning to make sense of what I'm saying. You generate expectations. Sometimes those expectations may be violated. When they're violated, you generate explanations for them. You try to figure out what was an error in your knowledge and reasoning. This is learning by correcting mistakes. Notice that you think about your own thinking, a step towards meta-reasoning, which is our next lesson. Please write down what you learned in this lesson.
Great. Thank you so much for your feedback.